Hi students, how are you all? Today we'll discuss about the torque numericals which are related to uniform meter scale. Yes, for that purpose I got a scale for you. You can see this, though it's not a scale, but let us consider this as a meter scale. This is a uniform meter scale. You can see 100 centimeter, 0 centimeter, 50 centimeter. I marked it so that I can discuss this with the help of this one. So this is our uniform meter scale. Now we will see some numericals related to this meter scale. First of all, if I put a fulcrum means I am keeping a support at 50 centimeter. So here is 50 centimeter. So I can see that at 50 centimeter I can balance the scale. Yes, at 50 centimeter I can balance the whole scale. Whole scale is completely balanced. That means this is called uniform meter scale. That's why it's uniform meter scale, because we can balance it from 50 centimeter. So when you are balancing from 50 centimeter, neither it is tilt this side nor it tilt this side. That means it's not experiencing any torque. Torque is 0. Let us draw this. This is my meter scale. 0 centimeter, 100 centimeter, and this is 50 centimeter. Here is the fulcrum F. So when your fulcrum is at 50 centimeter, neither it will tilt this direction nor this direction. That means total torque for this scale is 0. Now the question is that if the same scale, if I want to fix my fulcrum at 40 centimeter, here 40 centimeter, so we'll see that this side is become heavier. Now this is the torque it is experiencing. You can see, because this side is longer, so it become heavier. This is just 40 centimeter and this is 60 centimeter. Longer side, heavy mass. That's why this tilt this direction. So what is the torque it's experiencing? Now tell me. First it was supposed to be here like this, horizontal, complete horizontal. But when I placing my fulcrum at 40 centimeter, then we see this position. So it's coming down this direction. This direction is coming down. So it is clockwise torque. Correct. So it's clockwise torque. Let us draw this. So here is my meter scale. 0, 100 centimeter I am not writing. 0 centimeter, 100 centimeter. And 50 centimeter is the midpoint. But I am placing my fulcrum here at 40 centimeter. So when I am placing my fulcrum at 40 centimeter, you will see that the meter scale will tilt this way. Means this position will come this way. And this is the movement of clockwise. So we are getting a torque of this scale now. It was 0 here because it was balanced at 50, but now the fulcrum is at 40, so we will get some torque for this scale, and which is clockwise. Now the question is that how to find this torque for this scale which is in this position now. to find the torque, we will take the weight of this scale, into distance between the fulcrum and the midpoint. Yes, distance between the fulcrum and the midpoint. Don't forget. So, distance between the fulcrum and midpoint. Now, let us consider that the mass of this scale is, say, 80 gram. Mass of the scale is 80 gram. So, what is the weight of the scale? I taught you in the previous video that to convert mass to weight, just you write 80 GF. Yes, 80 gram is the mass, but when you are writing F beside this, now it is converted into weight of the scale into distance between the fulcrum and the midpoint. Where is the fulcrum? 40. Where is the midpoint? 50. 40 to 50, 10 centimeter. 10 centimeter. So we are getting 800 GFCM. This is the torque for this scale, which is clockwise. We saw that from the diagram. Now let us consider another example by placing this fulcrum at 70 centimeter. Now this is your meter scale, 0, 100 centimeter, and this is the midpoint, but where we are placing our fulcrum? At 70 centimeter. So when you are placing your fulcrum at 70 centimeter, obviously this side is longer, means heavier, so this scale will tilt this way. So this will be the position of the scale now. That means 0 is coming here now. This is 0 centimeter is here. So the scale will tilt this way now. Now if I ask you to find the torque, so torque for the scale equal to, same way, weight of the scale, mass of the scale is 80, so we'll write 80 GF into distance between fulcrum to midpoint. Distance between fulcrum and midpoint. What is the distance? Fulcrum is 70 and midpoint at 50. Distance is 20 centimeter. 20 centimeter. So 8 into 2, 1600 GF centimeter. But 0 is coming this way now. Now what is this direction? Clockwise? No, this is anti-clockwise direction. So we'll write anti-clockwise here. Anti-clockwise. Got it? Now, if you place the fulcrum at 100, taking the fulcrum at 100 now, let us draw the diagram. This is the scale now. 0, 100. Where is the fulcrum? Here is the fulcrum. Fulcrum at 100. 50 is the midpoint. So in this condition, obviously this complete side is there. So we will get our scale position this way. Means 0 centimeter will come here. Isn't it? Let me discuss that. Say this is the scale. You are keeping a support here. So what do you see? Obviously this will come this way. That means which direction it is? Is this clockwise direction? No. This is anti-clockwise direction. So we are getting a anti-clockwise torque here. So what is the torque for the scale? Weight of the scale, that is 80 GF. 80 GF into, what is the distance between fulcrum and midpoint? Where is the fulcrum? 100. Where is the midpoint? 50. So what is this distance? 50 centimeter. So we'll write 50 centimeter. So that is 4000 GF centimeter for this scale when you are placing your fulcrum at 100 centimeter. In this way, we can calculate the torque for a scale for different position of this fulcrum. And you must be very careful with this unit, GF centimeter. Units are important, otherwise the marks will deducted. I hope you understood. Now we will go for other examples where we will place different masses on this scale, extra masses on this scale. Let's discuss that. As I told you that I will show you how to calculate the torque for the scale if we place some extra masses on the scale. Let us draw it. This is my scale, 0, 100. The fulcrum is at 50 centimeter. Fulcrum is 50 centimeter. Now, I am placing a mass. Say this is the mass, which is 20 gram. I am placing it at 15 centimeter. We will find the torque for this. First of all, forget about all the external masses. Forget about this. See, is there any torque for the scale? Any torque for the scale is 0 here, because the scale is balanced at 50. So torque for the scale equal to 0. As we discussed, when you are placing your fulcrum at the exact mid of the scale, the torque experienced by the scale is 0. That is, at least torque for this scale is 0. Now you go for your external mass, that is 20 gram. Now we are finding the torque for that 20 gram. Same way, we will find the torque for this 20 gram. What is its weight? Mass is 20 gram. So what is the weight? 20 GF into distance. When you are finding the torque for the external masses, we have to take the distance between the fulcrum and that particular mass, external mass. The distance between the fulcrum and the external mass. Fulcrum is at 50. Where is the external mass? 20. So what is this distance? 15, 50. What is this distance? 35 centimeter. So we'll write 35 centimeter. So we are getting 700 GF centimeter. That is for this external mass. Now, think it practically. This is the scale which is completely balanced. So this is the scale which is completely balanced. Now if I put a mass here, obviously this side will get heavier and this will tilt this way. So when it will tilt this way, which torque it is? First it was like this. Now this position is going down. So this is the direction. This is the direction. This is anti-clockwise. Correct. So it will experience an anti-clockwise. So we'll write anti. Then let us hang another mass here, which is 30 gram, and it is at 70 centimeter. Now forget about all the other masses. and the scale. Just think in this way that only this mass is there with the scale. Don't think about this. Don't think about the scale. Just think about this one. For this mass, now this side has become heavy. For this mass, this side is getting some weight and obviously it will come this way. That means clockwise torque it will experience. So torque for 30 gram. Torque for 30 gram is, what is this weight? 30 GF into, as I told you, for the external masses, distance is fulcrum to that particular mass. Fulcrum to that particular mass is 50 to 70, that is 20 centimeter. 20 centimeter. That is so these are the torque for this one, and for this scale. For scale we are not getting any torque because the scale is balanced from this middle. Now, so this is clockwise torque. If I ask you, what is the resultant torque here? Resultant torque. What is the resultant torque? Resultant torque is, which is bigger, clockwise or anti-clockwise? This is anti-clockwise 700, clockwise 600. So obviously which is bigger? This is bigger. So we'll write 700 minus 600 equal to 100 GFCM. Which is bigger? Anti is bigger. So in bracket you must write anti. So this is the resultant torque experienced by the scale. I hope you understood. Let us consider one more example. Next example. Again another meter scale is taken. 0 centimeter, 100 centimeter. This is 50 centimeter. Now, the fulcrum is at 40 centimeter. This is the fulcrum. And here is a mass which is 20 gram at 65 centimeter. Here is another mass which is 50 gram at 10 centimeter. We'll find the torque for this one. First of all, let us consider that mass of the scale is say 80 gram. Mass of the scale is 80 gram and this mass, external two masses are given 50 gram and 20 gram. 50 gram is at 10 centimeter, 20 gram is at 65 centimeter. This is the whole sum and they are asking me, the question is whether this scale is balanced or not. After placing all this, whether this is balanced or not. Let us consider that. Balancing means total anti and total clock. I mean total anti-clockwise torque and total clockwise torque. If they are equal, then it is balanced. Let us calculate first. First we will take out the torque for the scale. Is there any torque for the scale or is 0? No, it's not 0 because fulcrum is not at 50. If the fulcrum is at 50, the thing will get balanced, the scale will be balanced and there will be no torque for the scale. But fulcrum is at 40 centimeter. So this side is heavier. And as I told you, when you are finding the torque for the scale, forget about other masses. Just think these masses are not there. Just forget about this. Say only this scale is there. And fulcrum is at 40 centimeter. In that case, what is the torque for this scale? First weight of the scale is 80 GF into, what is the distance? That when you are finding the torque for a scale, distance is from the midpoint to fulcrum. From the midpoint to fulcrum, that is 10 centimeter. 10 centimeter. That is 800 GFcm. As I told you, forget about these masses when you are finding the torque for the scale. Yes, when you are finding the torque for the scale, just see the scale, not other masses. If these masses are absent, only the scale is there, then which side is heavier? Obviously this side is heavier, longer, see. This side is longer, so this side is heavier. So obviously it will experience this torque. I mean, this is the scale when you are balancing at 40. So see which side is longer? That side is longer. Your right side is longer. So obviously it will tilt this way. That means clockwise torque. Yes, clockwise torque. So we are getting clockwise. Now torque for this 50 gram. So when we are finding the torque for this 50 gram, just think about this 50 gram. Don't think about this 20 gram. Don't think about the scale. Just think about this 50 gram. So for this scale, 50 gram you are fitting here. So obviously this side will be heavy. This side will get heavier. So it will come down this way. This way. So what is this direction? Anti-clockwise direction. So for this 50 gram, 50 GF into distance is from that mass to fulcrum. From this mass to fulcrum, 10, 40. Distance is 30 centimeter. That is 1500 GF. Yeah, 5 3 15, 1500 GF. And centimeter, this is anti-clockwise. Anti. Now forget about this. Just see this. Now we are finding the torque for this 20 gram. Forget about the scale. Forget about this mass. Just think about this. So when you are placing this 20 gram, obviously this 20 gram, this side will become heavy and this is the direction. So for this 20 gram, it will experience a clockwise torque. So torque for 20 gram equal to 20 GF into, what is the distance? I told you, for an external mass, distance is measured from the fulcrum to that external mass. External mass is 65, fulcrum is at 40. So what is this distance? 25 centimeter. So we are getting 500 GFcm. This is clockwise. Clockwise. Now, any other external mass? No. Two external masses were there. We have already calculated them. Scale also we have calculated. So now, total clockwise torque. What is total clockwise torque? This is clockwise, this is clockwise. 800 plus 500. 1300 GFcm. Total anti-clockwise torque. Total anti-clockwise torque is 1500. So are they equal? No, they are not equal. Total clockwise torque, total anti-clockwise torque are not equal. Since both the torque are not equal, so it is not balanced. It's not balanced. It's not balanced. Correct. If both the torque you find equal, then both the torque means clockwise torque and anti-clockwise torque. If both the torque are equal, then the whole scale will become balanced. But they are not equal, so it's not balanced. So what is the resultant torque? Resultant torque equal to, just minus it, 1500 minus 1300, 200 GFCM. Which is bigger? Anti is bigger. In bracket you write anti, that much. I hope that numericals related to this meter scale is cleared now. We'll go for few more examples. Let's see. In our next example, again we are going to consider an uniform meter scale, and we will place some external masses like the previous example, and the question is that one of the external masses, the measure of that mass is missing now. You have to calculate that. Let's see. Uniform meter scale. Now the fulcrum is at 60 centimeter. It is not at 50 centimeter. 50 centimeter is the midpoint, but it's not at 50, it's at 60 centimeter now. Now we are placing another mass here, 20 gram, which is at 20 centimeter. Here another mass which is not given, we have to calculate it, and this is at 80 centimeter. We need to find this external mass, and the mass of the scale is which is required here is 80 gram. So the question is, the whole system is there, this external mass which is not given, we need to find that. First of all, as I told you, is there any torque for the scale? Yes, obviously, because the scale is the position of the fulcrum is not at 50, it's at 60. So torque for the scale is there. What is that torque? Which side is heavier? This side is heavier. This is 60 and this is only 40. 60 to 100, 40, but this is 60. So this side is longer, that means heavier. So the torque is this way, anti. What is the value? Mass of the scale 80. So weight is 80 GF into distance. While finding the torque for the scale, distance is from midpoint to fulcrum. Midpoint to fulcrum, that is 10 centimeter, which is 800 GF centimeter. Now we'll get the torque for this 20 gram. As I told you, for which particular thing you are finding the torque, just think about that, forget about other things. Like if you are finding the torque for this 20 gram, just think about this 20 gram, forget about the scale, forget about this external mass. For this 20 gram, this portion is become heavy, so it will come this way down. Obviously, this 20 gram, for this 20 gram mass, this side is become heavier and it's coming downwards. So we are getting anticlockwise torque. See, anticlockwise torque equal to 20 GF into, what is the distance? Distance is from fulcrum to that particular mass. Fulcrum to that particular mass, that is 60 to 20 means 40 centimeter. 40. So 800 GFCM. This is anticlockwise. Yes, anti. Now torque for this mass. When you are finding the torque for this mass, we'll forget the scale, we'll forget this mass. Just think about this. So when you are placing an external mass here, obviously this portion become heavy and it tends to come down this way. It tends to it's coming down, that means clockwise direction. So for this we are getting a clockwise torque. What is that clockwise torque? Say what is the mass? M. Say what is the weight? No need to convert it, just write M into what is the distance? Fulcrum to that particular mass, 20 centimeter. 20 centimeter. So we are getting 20 M, but this 20 M is clockwise. Not over yet. They said that in the question it is given that the whole system is balanced. The scale is completely balanced. So when the things is balanced, then total anti equal to total clockwise torque. Total anti-clockwise torque equal to total clockwise torque. What is the total anti-clockwise torque here? Total anti. That means 800, 600, 1600, and total clock 20 M. 20 M. Why I made them equal? I told you in the previous example that if total anti-clockwise torque and total clockwise torque, if they are equal and same, then the thing becomes balanced. And in this question it is already given that the whole system is balanced. So that's why total anti-clockwise torque equal to total clockwise torque. So that's why 1600 equal to 20 M. So M equal to 1600 by 20. So 0080 gram is the required mass. So we need to find that is 80 gram. Understood? Fine. Now let us go for another example. In this example, the mass of the scale is only missing. We need to find the mass of the scale. Other masses are also there, but the mass of the scale we need to find. Let's see. This is the meter scale. And the fulcrum is at 70 centimeter. And mass of the scale we need to find. And this is the extra mass which is given, and say this is 70 gram and which is at 80 centimeter. Now in this system, first of all we'll find the torque for the scale. And I told you, when you are finding the torque for the scale, forget about other masses. Like just think about this scale, forget about this. Say this mass A is not there. So what is the torque for this scale? Torque for scale. What is the mass? We don't know, M. Just write M into distance. Distance from the midpoint to fulcrum. Where is the midpoint? 50. Midpoint to fulcrum, that is 20 centimeter. 20 centimeter. So we are getting 20 M. 20 M is it is clockwise or anti-clockwise? Which side is longer? This side is longer? No. This side is longer. So longer means heavy. So we are getting anti-clockwise. Anti. Now torque for this 70 gram. And we'll just think about this 70 gram. We'll not think about the scale. So 70 gram is fitted here. So this side will get heavier and it will come down. So when it's coming down means this direction is clockwise direction. Clockwise direction, and we are getting a clockwise torque for this 70 gram. So how to find that torque? 70 GF into, what is the distance? Fulcrum to that mass. 70 to 80, 10 centimeter. equal to 700 GF centimeter, and they said that it is balanced. The system is balanced. When the whole system is balanced, that means total anticlockwise equal to total clockwise. What is the total anticlockwise torque? 20 M. 20 M. What is the total clockwise torque? 700. So M equal to 700 by 20, that is 35 gram. So we got the mass of the scale 35 gram. And why I made them equal? Because total clockwise and total anti-clockwise are equal, since it is mentioned in the question that it is balanced. So in this way we can go for all the numericals of our textbook. And one more thing, we should remember that while finding the distance of the scale, distance between the fulcrum and the midpoint, and when you are finding the distance for the external masses, distance means fulcrum and that particular mass. Here it's midpoint. So for the scale, distance means fulcrum and the midpoint. But for the external masses, distance means fulcrum and that particular mass. Just you have to remember that. Don't be confused. Easy concept, easy sums. Try all the sums of your textbook. Thank you.